All right. So we have a substitute cameraman here. Hope our regular guy must be a little late, but I think we can forge ahead. So I don't have any, you don't have a homework assignment today, so I assume there's no questions. I mean, did you like read over the material in your spare time just because you liked it and you have some questions about reading in the book? Yuck, yuck. Okay. Anyway, at the end of class last time, we were just getting ready to, we had just proved I think we had proved one of these, or, well, I don't remember what we did, but at any rate, we went over the definition of divides, and we looked at a few theorems for divides, and we're just getting ready to prove 15.82. And this is, so we're going to prove transitivity. If D, so let's take a look at 1582. If D divides C and C divides B implies D divides B.
No way.
Transitivity of divides. And of course, let's look. In order to use transitivity of divides, we're obviously going to have to use the definition of divides. Now, divides is a little bit different from max in that, remember last time we said that we don't have a theorem that says x, I mean, we don't have a definition that says x max y equals something. But here we do have such a definition for divides, right? I mean, we do actually have C divides B equivals. There exists a D, range true, such that D times C times D equals B. Okay, so here we go, 15.82. So we're going to prove 1582, which is D divides C and C divides B implies D divides B. Okay, so, and the way we're going to do this is, what's our favorite technique for implies? Yeah, assume the conjuncts of the antecedent. Okay, so we will assume, we got two conjuncts here. Now, but the way we're going to do this is, let's go back to the definition. We're actually going to use, a little bit of informality here. We're going to use the definition of divides, okay? So for each one of these conjuncts, okay? So first let's do it for this left conjunct. So by 1577, which is the definition, by 1577 and D divides C. All right, so here. Now what does it mean for D divides C? According to 1577, it means they're what? That equivals what? Yes, some integer. You're right. Okay, so, and that's right. So just right there. By 1577 and D divides C, there exists some integer. There exists some integer. Now what we're going to do is we're going to give it a name. All right? I mean, because it says there exists one, so we're going to write one down. We're going to give it a name. And we can do that by 1577. There exists some integer. Let's call it, we're going to use hat, D hat. Okay? Such that what?
D times D hat equals C.
Yeah, that's correct. Now, does everybody see how we're able to write this down? So now what we can have is, we can have this as one of our assumptions, all right, in our proof, because we're assuming the conjunct. So we can use this as one of our conjuncts, okay? And similarly, what about the other one? Similarly, there exists, similarly.
C times D hat equals B.
Well, yeah, a different number. C hat. There exists some C hat. There exists a C hat such that, now what will the C hat one satisfy? C times C hat equals B. Are you with me? Okay. And now what we're going to do is, we're going to prove the right-hand side. But we have multiple techniques here. Two for the price, another 2 for the price of 1. 2 techniques in 1 proof. How do you suppose we're going to prove this is true? So we want to prove that this is true, right?
So
You using these as if they were axioms, right?
So we use 3.7.
Yeah.
True implies that.
Yeah. Okay. So assume the context. So to prove D divides B, use 73? Is that what it was?
Mm-hmm.
Use 3.73 and prove, and then so what do we prove instead?
True implies D
True.
divides B.
Exactly, and prove true. Does the camera get over here?
Mm-hmm.
And prove true implies D divides B. All right? Is everybody clear on this? Now there's 2 ways to do this. We could either start with this and get it to follow from true, or we could start with true and get it to imply this. And actually, this time
Start with true.
we're going to start with true and get it to this.
Makes a lot of sense.
Okay, so here's our proof. Actually, this whole thing is the proof, but this is setting it up to prove this. But, this is the proof of that. Anyway, all right? Okay, so let's start with true. Now, equals. Now, obviously, we're going to start pulling some rabbits out of a hat if we start with true. But on the other hand, we have some really good candidates here, right? Because we can assumption C times C hat equals B, right?
Should we just assume both of them right now, or are we not going to?
Well, we'll do them separately. Assumption C times C hat equals B. So this will be C times C hat equals B. And now this equals by assumption what? Because now we have a C, right? Okay, so this will be assumption D times D hat equals C, and we can substitute equals for equals, and therefore this will be D times D hat times times C hat equals B. Lots of hats.
how do we get rid of C hat?
Weakening.
Yeah, now, now this is really pulling a rabbit out of a hat.
Prove that C hat equals 1.
What we're going to do is we're going to write this. I don't see how you could see this, actually. So you know our 1-point rule?
Yes.
What is our, we're going to use the 1-point rule, but we're going to go backward. Here, let's look at actually let's bring up the 1-point rule. I think that'd be good to look at.
Is it 8:15?
Well, man, you're off by 1, but that was really good. Yeah, let's take a look at our axiom 1-point rule. Our axiom 1-point rule says, provided that x does not occur in E, we have this 1 point here, star x, range x equals E, body P equals P with x replaced by E, right? But now what we're going to do is we have this, we're going to go backward. Normally the way you use the 1-point rule is you start with, you have the left-hand side and you write down the right-hand side. What we're going to do is we're going to start the right-hand side and we're going to write down the left-hand side. And we're going to use, and for the star, and for the star we're going to use there exists.
So there exists an X?
Yeah, we could call it anything we want. I used K, so just to keep my notes.
Okay.
Because it's a dummy variable, right? So we're going to claim, equals by the 1-point rule, 8.14.
So there exists a K, range K equals
Yeah, there exists a K, and then range, and then the range has to be K equals something.
K equals D hat times C hat.
Very good. Now, how did you know that?
We need to get rid of it. That needs to
Because
be
that's what, yeah. So K equals d hat times c hat, and then body, so, and then body would be what? D times what? K equals B. Is everybody clear on that? D times K equals B. Oops. Now, how's that? That's pretty cool, right? And the way to, I mean, if you're used to doing it the other way around, just to see that this is true, just if this is what you would have for the one-point rule, it's easy to go this way, right? We just went the other way. So there exists a K, K and a D. All right? But now, if you can figure out this next rule, this next thing, it'll be really nice if you can figure out what we have to do next. Because what are we working towards? Let's look ahead at what we're. Let me see if you can come up with this next step. You guys out there, watching this on video, what do you think the next step is? Now look, what are we headed for? What are we? You know, whenever you do these proofs, what are you looking? We want to get to D divides B. Well, to get to D divides B, we have to have. Yeah. How do we get to D divides B? Yeah, there exists, we have to get to, there exists a K, right.
Can you pull up the definition of divides?
Oh, sure. Let's look at the definition of divides.
Oh, no,
That's it, okay.
Can we do range weakening?
Oh man, that's so good. Because what actually we would have it if this were what?
True.
If this were true. We would have it if this were true. Now, is this the K? Range true, D times K equals B. But can you just willy-nilly get rid of this?
Yeah, you have to imply.
But you have to have an implied. But that's okay because we're starting with true imply. We want the implies. Oh man, that was so good. Yeah, so let's look at range weakening. 9 here. Yeah, let's look it up here. So 925 says range. Yeah, this implies by range weakening. Here we go. How are we going to do this now? What should we use for R and Q? I mean, we know what P is, right? P is, we know what P is. P is D times K equals B, right? The body is the same in both, right? So what do we, this range weakening, 9.25, with RQ replaced by what?
K equals D hat times C hat.
And, yeah. So it's K equals D hat times C hat and true. Now, if that's the case, what do we have? We would have, there exists an X, range, it would be, if we were to write this out, what would we have? There exists an X, range,
K,
yeah, there exists,
D
yeah,
hat times C hat, body P,
implies,
there exists a K, range, K equals D hat times C hat, or true, body P.
let's write this out. Which is what? Range D times K equals B. Right?
Yes.
But now we know that anything or true is true. Is that what you were
Yeah, that's what I'm
saying? What we should do?
Weaken it again.
No, it's not weakening. It's not weakening.
It's just
Yeah, here, it's, yeah, boom, yeah. So let's just end the hint here. Oh, and
yeah. And it's like 3.
here we can say and 0 over or, yeah.
No, that's it. No, we do that.
So that will end the hint because we know that this or this is true. So we know this implies, well, we're not quite done yet because this equals, no, I'm sorry, this implies what?
There exists a K.
There exists a K. Range true, okay, because that's true. Body
D times K equals
D times K equals B. And now this
5, 15, 77.
equals by definition. definition 15.77, D divides B, and we're done because we said that we set it up that we're going to prove that by true implies that. Ooh, wow, pretty good. Huh? How about that? We'll go all the way back to chapter 8 and 9, do all these general ones. Pretty cool, huh? Now, 1579. 1579 is a homework problem, okay? So you can look forward to that. All right, and the next, so any questions about this? Are we good? Okay, now the next topic that we want to look at is, well, let's read through a few of these theorems. We just proved 1582, transitivity. 1583, does that make sense? B divides C and C divides B. That equivales B equals C or B equals negative C, right? Makes sense? One can't be bigger than the other, right? And then, well, in absolute value, in magnitude. 1584, B divides C implies B divides C times anything. You know, if B divides C, it divides C times anything, all right? So we should be able to prove that. 1585, B divides C implies B times D divides C times D. That's kind of like a cancellation law, right? And then 1586, 1 is less than B. In other words, B is greater than 1. And B divides C implies B does not divide C plus 1. Ooh, that's not as intuitive.
It's really weird.
It is weird. But if B is bigger than 1 and B divides C, it can't divide C plus 1.
Yeah, makes sense.
Right? If you add 1, yeah.
It's not small.
But that's ooh, that'd be tricky to prove, don't you think? And here's another theorem. This is the division theorem. Given integers b, c with c greater than 0, there exists unique integers q and r. Q stands for quotient, r stands for remainder, such that b equals q times c plus r. We've actually seen this before. We had the algorithm that calculated the division, the quotient and the remainder. Remember that?
Yeah.
And we used this expression before. So here we have, this is the division theorem. Now, the next thing that we want to look at is the greatest common divisor. Now, you guys have done greatest common divisor, I'm sure, in manipulating fractions, right? So, here's the definition of, before we do the definition of greatest common divisor, which is 15.92, let's take a look at the definition of divides, okay? So definition of divides and mod for operands B and C. So here, remember that whenever we use divides here, we're dealing with integers, okay? So because this whole chapter is a theory of integers, so we're not dealing with numbers that have fractional parts. Okay, we're not dealing with rational numbers or real numbers, okay? So B divides, B divided by C equals Q, and B mod C equals R, where B equals Q times C plus R, and 0 is less than or equal to R is less than C. Okay, so this is what it means to this. Yeah, and this is what it means to divide. This is what divides means. Okay, what it means is that if you take B divided by C, the number that you get, Q, which is the quotient, has to be such that B mod C equals R. So R is the remainder, right? B mod C is the remainder that you get when you take B divided by C. All right? And then what has to happen, well, this is that same division expression, right? Where B is the quotient times C plus the remainder, and the remainder has to be greater than or equal to 0 and less than C. Right? Otherwise, it's not the right kind of remainder. You know, like you could say you could say, you could say 15 divided by 2 equals 6, remainder,
Negative.
well, if 15 divided by 2 would equal 6, remainder 3, right?
Right.
But that doesn't make sense, because that's not right, because
You can still.
because this remainder has to be greater than or equal to 0 and less than 2, right? So this isn't correct. Instead, 15 divided by 2 equals 7, remainder what?
1.
Yeah, remainder 1, right? So so in order for this remainder to be the remainder, it has to be greater than or equal to 0 and less than or equal to the divisor, right? So here the quotient would be 7, Q would be 7, and R would be 1, right? So B would be 15 and C would be 2. Does everybody see that? Okay?
1590.
That's 1590, and that's the definition. So we don't prove that. That is what has to be, those mathematical equations are what have to be true in order for Q to be the quotient and R to be the remainder.
What
When
does
you
mod stand for?
the remainder when you divide B by C, modulo,
Modulo.
right?
That's what it means, literally remainder?
Yes, it literally means remainder. And the way you do, what is that in do you know how you do the mod? Yeah, in C++ and Java, this is the mod. So that you're in math, C++, Java. In math, it's mod. In C++ and Java, it's the %. So, okay. There's some programming languages where you actually spell out mod, M-O-D. It's nice. The ones that are more closely aligned with mathematics notation. It's unfortunate that there was a period in time in computer science history where the programming languages, as they were being developed, the people who developed them were more kind of like scientific or mathematical. And so they had the notations, they didn't mix up equals, this colon equals was how you did gets, how you did the assignment operator. Those languages had superior notation compared to this ugly C++ and Java, where we have these weird symbols that don't line up with what their meanings are in mathematics. And it's unfortunate that history took that turn, but it's with us, and so we just have to live with it. So then 1591 is a theorem, B equals C times B divided by C plus B mod C. And it falls from 1590. But the main thing that we want to study now is greatest common divisor, which is 1592, definition of GCD. And here is the definition of GCD. Now, you guys, here, let's do some examples. 1592. And I think you'll be able to see what it means. So B, GCD, C. So GCD is a binary infix operator between two integers. Now, how do we read this? It's the max over D. So we're quantifying the, okay?
Yeah.
So it's the max over D.
Where D divides B and D divides C.
Where the range D divides B and D divides C of D. So it's the biggest D that divides both of them. It's the greatest one that divides both. That's why it's called the greatest common divisor that divides both, all right? But now what has to happen is B and C are not both 0. One of them can be 0, but both of them can't be 0. So let's do an example. What's 1 GCD 5?
1.
That's 1. Is everybody clear on this? Because 1, yeah, are you with me? Because 1 divides 1 and 1 divides 5, and it's the biggest one that divides them both. How about 0 GCD 5?
Does anything divide 0?
Yes, anything divides 0. Yeah, this is 5. Is everybody clear on that? All right. And how about 24 GCD 30? What's that? It's the biggest number that divides both of them. Well, 1 divides both of them, 2 divides both of them, 3 divides both of them. 3, is that the biggest one? 6, you say, right? It's the greatest one, okay. How about negative 24 GCD 30? That's still 6. Is everybody with me on that? Okay. And how about 24 GCD negative 30? That's still 6. And how about negative 24 GCD negative 24? What's that? Oh, sorry. GCD, sorry. 30. That's still 6. Is everybody clear on that? And how do you, where do you use GCD? The way you'd use GCD is, suppose you have a fraction, 24/30ths. Then what is this? I mean, how do you reduce this? You take the GCD of 24 and 30, which is 6, and you do what? You do 24 divided by 6. You divide both sides by the greatest common divisor. And that's how you get it to lowest terms, right? So that's 4/5. So that's where GCD comes in handy. You learned that when you dealt with fractions. All right? Now, what about 1594? Definition of, now what does LCM stand for? Least common multiple. Oh, that should be spelled out on the equation sheet, huh? It should be definition of greatest common divisor, comma, GCD. Anyway, LCM is, yeah, GCD.
Same with mod then.
GCD, greatest common divisor. And so let's do 1594 examples. And this is least common multiple, LCM. So what's 12 LCM 18? Now what does it say the least common multiple it is? Ooh! Now instead of the max over D, this is the what? The min over K. But K has to be what? Positive integer, right? So it's the min. So it's the min, but it can't be min. It can't be a negative number. So it's the min over K, such that what?
B divides K.
K and C divides K of K. So it's the min K. All right. For B not equal to 0 and C not equal to 0. So now neither here it's okay for one of them to be 0. Here neither of them can be 0. Right. Are you with me on that? All right. And then, oh, and also, by the way, there was one thing we didn't mention. When they are both 0, 0 GCD 0 is 0. Okay? And then if one of these is 0, B LCM C is 0. All right. So what is 12 LCM 18? 12 LCM 18 is 36. So now this is, yeah, so how did you get that?
The least of all the things
that these will go into. It's the smallest one that both of these will go into. 12 will go into 36 and 18 will go into 36. And furthermore, 36 is the smallest number that they will go into. And how do you use this when you do fractions? It's like if you have 5/12 plus 5/18. This is when you want to combine them. You want them to have a common denominator. So what happens is, so what this is, so the this LCM is what you choose for your common denominator. So this is, so 5 over 12 is what over 36? It's 15. And then 5 over 18 is what over 36? 10. Okay, and then you can add these, 25 over 36. Okay, so here again, you guys know how to, you've done this with fractions before, but there is the formal definition of LCM. All right? So let's take a look at some theorems. 1596 is symmetry of GCD. And actually, 1596 is a homework problem. Proof of 1596 is a homework problem. So how will you solve that? How will you do that? B GCD C equals...
Start with one side, get the other.
Start with one side, get the other, use the definition. But here we have a definition, and we can say equals. Use some sort of symmetry with max or min or something. Yeah. Okay, so that should be pretty straightforward. And 1597 is associativity. That's interesting, huh? B GCD C. If you do the GCD of that, and then you do that GCD D, that's the same thing as doing C GCD D first, and then doing B GCD that. Okay, so it's associative, and it's also idempotent, but it's not quite idempotent because we have to throw in an absolute value there. B GCD B, like if B is -5 GCD -5 is what? It's +5. It's not -5. So we have to throw in the absolute value there. If it were strictly idempotent, it would be B GCD B equals B, right? But it's idempotent, but with an absolute value. And then 1 GCD B equals 1. That's another homework problem. The 0, 1 GCD B. This is a little tricky. You might, when you go through this, don't wait till the last minute to prove this one. You might have to think about that one a little bit. And here we have the identity element. 0 is the identity for GCD. Yeah, for addition too, and it's also. But here again, we got to throw in this absolute value. And then what about 101? B GCD C is the same thing as equals the absolute value of B GCD, the absolute value of C.
Like
so it does. Yeah. Mm-hmm. And then B GCD C equals. Now, this is the conjunctive meaning, right? Because this is equals, not equivales. Are you with me? So the conjunctive meaning is B GCD C equals B GCD B plus C and B GCD B plus C equals B GCD B minus C. But that makes sense, right? Because if you add, well, think about it. And then B equals A times C plus D implies B GCD C equals C GCD D. Ooh. Yeah, that is interesting. Okay, now, so those are some theorems for the greatest common divisor, and now the next thing we're going to do is, and so those are due on Thursday, and now the next thing we're going to do is look at a famous algorithm for computing the GCD. And here it is. This algorithm is called Euclid's algorithm, which is quite a remarkable algorithm because Euclid, of course, was an ancient Greek mathematician. But he had this procedure using multiple subtractions for calculating the GCD. And the algorithm is in our textbook, and I've reproduced it here on the slides. And so let's take a look at what it does. In the end, what it does is the postcondition is that x equals y and y equals b GCD C. So what the algorithm assumes is that b and c are given in the beginning, right? And what we want to do is we want to calculate b GCD C, all right? And so what we do is, and so our precondition for the whole thing is that B is positive. Are you with me? So we're going to require that B is positive
C is positive.
and C is actually both of them. So we're talking about the GCD of two positive numbers. Now, you know, if they're negative, don't we have some theorems that say,
Absolutely.
yeah. Okay. But at this point, we're going to assume that they're positive. And what I want to do is, you know that here, I want to trace through, I think we have time to trace through and see how the algorithm works. Next time in class, what we'll do is we're going to prove it. We're going to prove it using the 4 steps. Yeah. Okay, so let's just take a look and see how it works. So now, you know that, what is 21 GCD 36? What does that equal? What is 21 GCD? Just before we do it. Yeah, that's 3, right? Is everybody clear on that? So the way this algorithm is going to work, this 21 is our B. We're going to assume that B has the initial value 21 and C has the initial value 36. And in the end, what should we have? In the end, what does it say we should have? We should have what? What does it say, the postcondition?
X equals Y.
Yeah, we should have X equals Y equals 3. That's what we should have. Are you with me? They should be equal to each other and equal to the GCD of B and C. All right? Now, so the way we're going to do this, we have two. Now, I wish that our GCL, that our author would tell us the types of X and Y, but the types of X and Y are int. Okay, so it's int X comma Y. So what we have here, so let's just trace out the values. So here's X and here's Y, and we are going to assume that, well, here's X and here, and we're going to assume that B and C are 21 and 36. So the very first thing that happens is X comma Y gets B comma C. So what does that give to X and Y? 21 and 36. Are you with me? Now we claim that we have this invariant P, X GCD Y equals B GCD C. Now is that true? Does X? Well, of course, because we just said X and Y to B and C. So X GCD Y has to equal B GCD Z because X equals B and Y equals C, right? And furthermore, X and Y are both positive because we said B and C had to be both positive, right? So that's our invariant. Now, watch how this works. Do X, so our guard is what? X is not equal to Y. 21 is not equal to 36, true or false?
That is true.
That is true. So now we have guards. If X is greater than Y, X gets X minus Y. Guard, if Y is greater than X, Y gets Y minus X. So basically what are we doing? We're taking the larger one and subtracting it from the smaller one. So in this case, X is 21, Y is 36. So is the first guard true? 21 is greater than 36, yeah?
No.
No. 36 is greater than 21, yeah?
Yes.
So what happens?
Y gets
Yeah.
So 36 minus 21 is what?
15.
Now, does everybody see how that worked? And then in the if, we go back up. X is not equal to Y. 21 is not equal to 15. True or false?
True.
True. So what happens? If X is greater than Y, 21 is greater than 15?
Yes.
Ah, so what happens?
21 becomes 6.
21 gets 6. Because 21 minus 15 is 6. Are you with me? We go back up. X is not equal to Y. 6 is not equal to 15, yeah?
Yeah.
So what happens?
Second one.
15 becomes 9.
15 gets 9. All right? And then 6 is not equal to 9. What happens?
9 gets 3.
9 gets 3.
And then
6 is not equal to 3.
X gets 3.
X gets 3. Now, X is not equal to Y.
False.
False. Ah, so we terminate. And what happens? X equals Y equals 3. And furthermore, it's the GCD. Now, is that slick or is that slick? Now, Euclid, Greek, before computers. Subtract. And you just think he had to do that with, I was going to say he had to do it with Roman numerals, but that was Rome.
Yeah.
Was Greece before Rome? What numbers did they use Roman numerals in
How it
Greek? Yeah, I don't know. But I mean, to be able to come up with that, that's pretty good, huh? And how many times did it loop? You know, it looped 5 times, right?
Yeah.
1, 2, 3, 4, 5. So it looped 5 times. Oops. So it loops 5 times.
What's the big O for that?
Ooh, that's a really good question. What is the big O for that? It's whatever, it depends on, oh, that's a tricky one.
I think it's
Worst case it would be, you would subtract 1 every time.
that's the greatest number.
So it's it's big O of the greatest number, worst case.
Makes sense.
Oh, nice question. Yeah. So what we'll do, so we understand Euclid's algorithm. I mean, we've seen an example of it. And then what we'll do, it'll probably take us most of the class next time to actually prove it. So, that's all, folks. That'll be it.